Hi everybody and welcome back. It's model creation time. We use the same architecture as we used in the classification task with some small adaptations. At first, instead of predicting a binary label, we need to estimate the location of the heart. Therefore, we need to change the number of out features from 1 to 4. Second to that, as we are dealing with continuous values, the L2 loss or mean squared error will be used instead of the cross entropy. Okay, let's define the model. We can call it cardiac detection model, which as usual when working with PyTorch Lightning inherits from pl.lightning module. At first we define its constructor. We don't need to pass any arguments to the model, therefore it only accepts the self-argument. Above all, we call the constructor of the parent or superclass to make sure we don't forget it. Now we use tortuition.models.resnet18 to load our model. Additionally, we pass pre-trained equals to true. As our dataset is really small, we shouldn't train from scratch, or in other words, with randomly initialized weights. By passing pre-trained equals to true, PyTorch loads the model with the weights resulting from training it on the ImageNet dataset. This is called transfer learning. Next, we need to change the number of input channels in the first convolution from 3 to 1. When remembering the network architecture shown in the last project, we know that we can access the first convolution by self.model.conv1, which we now change to be a torch.nn.conv2, the object with 1 input channel, 64 output channels, a kernel size of 7 × 7, a stride of 2 × 2, padding of 3 × 3, and last but not least, we set bias to false. Perfect, this step is done. Next, we need to change the out features of the last fully connected layer. Again, recapping our model structure, we know that we can access this layer via self.model.fc. We now assign a new linear layer with 512 in features and 4 out features to this object. Alright, we successfully adapted the model to our specific task. Note that when changing the structure of a particular layer, PyTorch needs to reinitialize the weights of this layer to random values. This means that in our case, the first convolutional and fully connected layer don't have the weights resulting from training the ResNet on ImageNet anymore. Of course, all other layers still have those weights. Alright, our network is now ready to tackle the task of heart detection. Okay, last but not least, we can define the optimizer and loss function. Regarding the optimizer, we simply use the Atom optimizer again. Once more, you can access it via torch.optim.atom, to which we at first pass our self.model.parameters and next the initial learning rate, which we define to be 1e-4. As already mentioned, we use the torch.nn.mse loss as our desired loss function. Perfect! Our model initialization is complete. Next, we define the forward function responsible to compute the prediction for the given data point. Let's directly return the output of self.model data. Now we are ready to define the training step, which accepts, of course, self, the current batch, and the batch IDX. Before doing anything else, we extract an X-ray image and corresponding label from the past batch. Subsequently, we convert the label or bounding box coordinates to a float which is needed for loss computation. After that, we are already ready to compute the prediction by calling self, to which we pass this particular X-ray image. Based on this prediction, we can now compute the loss by calling our predefined loss function, to which we simply pass our prediction and the corresponding label. Let's log this loss by calling self.log, use train loss as unique identifier, and of course our loss. Additionally, we can use TensorBoard to visualize some images with predicted and ground truth bounding boxes. Since this operation takes a bit longer, we perform it only every 50 batches. First we check whether our batch IDX modulo 50 is congruent to 0 to make sure that only every 50th batch is used. Then we call a function which we will later code ourselves called log_images, to which we pass the X-ray images copied to the CPU, the corresponding predictions and labels also copied to the CPU, and a unique identifier, let's call it train in this example. Copying the data to the CPU is necessary to visualize it. Last but not least, we return the training loss, based on which PyTorch updates our weights. Cool, the training step is complete. Let us quickly define the validation step by copying our training step and rename the necessary parts of it. At first, we of course rename the function from training step to validation step. Next, we exchange the unique identifier in the self.log call to val_loss. Last but not least, we replace the string train in the call to the log images function by val. Alright, the validation step is also complete. Now it's time to define our log_images function. We write def log_images, which accepts at first of course self, followed by a batch of X-ray images, the corresponding predictions and labels, and last but not least, the unique identifier. Above all, we create an empty list called results, which will store the X-ray images with visualized bounding boxes. To do so, we create a loop in the range of 4, where we at first extract the predicted and ground truth coordinates. Let's define a variable called coords_labels, which will take the bounding box coordinates of the ith X-ray image. Next, we define coords_breadth, which will take the corresponding prediction. After that, to get a much more decent visualization, we have to unnormalize the X-ray image, as it will otherwise look kind of strange. To do so, we can simply multiply the corresponding image with the pre-computed standard deviation and add the mean afterwards. Let's access the ith X-ray image, multiply the pixels of this image with 0.252, and finally add the mean, which was 0.494. Subsequently, we convert it to a NumPy array to allow plotting and get rid of the channel dimension. Now we extract the coordinates from labels and predictions to finally draw them on the image by using cv2.rectangle. Let's define x0, y0, to which we assign coords_labels 0, which we will at first convert back to an integer, and subsequently get rid of all PyTorch specific attributes. When calling .item, you simply extract the scalar. To get y0, we call coords_labels 1, which we will again convert to integer and get rid of everything else. To get x1 and y1, we can simply copy the statement from above and replace 0 by 2 and 1 by 3. Now we override our image array by calling cv2.rectangle, to which we at first pass the original image, next the tuple describing the top left corner, and subsequently the tuple describing the bottom right corner. Additionally, we can define the color of the bounding box. Let's use black, which is identified by 0 times 3. Last but not least, we set the line width of our bounding box to 2. Alright, we successfully drew the ground truth bounding box on our X-ray image. To visualize the prediction, we simply copy this complete code block, replace chords labels by chords pred, and change the color to white by using 1 times 3. Let us now append this result to our results list. In fact, to create the grid later, we directly convert the image back to a torch.tensor and add the channel dimension. To convert our results list into a beautiful grid, we can use torchvision.utils.make_grid, to which we at first pass our results list and next the number of desired columns. In our case, to create a 2 times 2 grid, we pass 2. Now all we have to do is to lock this grid. However, simply using self.lock is not sufficient to perform this operation because it was created for scalars. In order to lock this grid, we have to access our original logger object. To do so, we can write self.logger.experiment.add_image, to which we pass at first a unique identifier, name in our case, next the grid, and last but not least the global step. You can access the global step of your training by simply accessing self.global_step. Alright, perfect! Our logging routine is complete. Last but not least, we only have to define the configure_optimizer function, which simply returns a list containing our optimizer. Perfect! Our cardiac detection model is complete. Great job! We can now create an instance of this model by at first defining the model variable and simply call cardiac detection model. Let us store the top 10 checkpoints with the lowest validation loss. Therefore, we define our checkpoint callback by using the model checkpoint class, to which we pass at first monitor as validation loss or val loss. Next, define the top k checkpoints to save, in our case 10. And last but not least, mode equals to min to save the checkpoints with the lowest validation loss. Now all we have to do is to define the trainer and fit the model. Let's use PyTorch lightning.trainer, to which we pass at first the number of GPUs, 1 in my case. Next, our TensorBoard logger, which accepts the desired log directory. Let's simply call it logs. Subsequently, the logging frequency, which I want to be 1. Our checkpoint callback. And last but not least, the maximum epochs, which I want to be 100. Now we are ready to fit our cardiac detection model. We at first pass, of course, our model variable, followed by the train loader, and last but not least, the validation loader. Alright, let's start the training. As you can see, the training is really fast and you can train this model on a CPU without any problems. In the meanwhile, let's have a look at our TensorBoard. You can see that both train and validation loss have decreased rapidly. When inspecting our example grids, we can observe that after only around 2500 steps, the bounding boxes were quite accurate. We can also scroll through the previous steps to inspect how the model performed in the past. As an example, after only around 1200 steps, the predictions were catastrophically wrong. Alright, that concludes this lecture. In the next lecture, we will evaluate our model. Thanks!